recording. All right, so we want to talk about question number 2, okay? So question number 2, how many sides does that nonagon have? 9. So a nonagon, 9-sided figure, looks like this. Let's see here. All right, and it's regular, correct? That's key to this problem. Meaning that all of those sides are the same, right? Meaning there exists in a regular polygon one of these things. Do you remember what you call J to G? Say again? Circumscribed circle. Okay? So, the angle right here, okay, would you agree that that angle is a portion of 360 degrees? It's a ninth of it, right? Would you agree that this is another ninth of it? Yeah. Another ninth of it, right? And a ninth of 360 is 40 degrees. Is that okay with everybody? Yeah. So when I look at this problem here, I'm thinking that is kind of like a dial on a radio or something like that. And I can only take D and put it on C once it like turns and clicks to C. Does that make sense? Okay. So I need to rotate this dial 40 degrees counterclockwise to get D to click to C. How many degrees then do I need to get D to go to C, and then B, and then A, and then I? 40 times how many? 8. 1, 2, 3, 4 positions, right? So it'd be 40 times 4, which is 160. Now we're looking for, because they don't say it, we're looking for counterclockwise rotation, right? If they said clockwise, you'd go 40, 80, 120, 160, 200, right? Does it get you to the same spot? Yeah. So rotating something counterclockwise 160 degrees is exactly the same as rotating something clockwise 200 degrees. What do they add up to? 360. And that should always be the case. We call those, in trigonometry, we're going to call those coterminal points. Co meaning together, terminating means, or terminal meaning terminating or stopping. And obviously they're both points. So going in one direction, I can get to I through 160 degree rotation. Going the other direction, I can get to I going 200 degree rotation. Yes?
So why is it that you have to go kind of like for yesterday's? Why is it you have to like?
It's just the way that the math community says that we're all going to do it.
So could you go clockwise? Like what is it?
So, I mean, if your answers are predefined like it is here, obviously I would mess it up. What happens so this is going to eventually take you into like a trigonometric concept. We talk about in trigonometry, so I'll show you this shape real quick. All right, so in trigonometry, we learned that thing right there. It's called a unit circle, okay? Basically, it's just a way of developing ordered pairs on the coordinate plane between -1 and 1 on the x-axis and 1 and 1 on the y, -1 and 1 on the y-axis, okay? For a certain angle. So what that's doing for me right there, if I say sine of 30, it's going to be 30 being 30, or sorry, I guess it'd be 30. Let's do 30. Let's get that up here. So sine of 30, because this is a 30-degree angle, right? It's going to spit back that y value that's associated with this point right here on that circle, okay? And if you type in your calculator sine of 30, it's going to spit back 1/2. Does that make sense? If you type into your calculator the sine of 500, it's going to spit back 0.707, which is the y value of that right there. Does that make sense? Okay, so this is the unit circle that allows us to evaluate the sine, cosine, tangent, secant, cosecant, cotangent at multiples of 30 or 45 very, very efficiently, very, very quickly. Okay? In the development of that, we say that an angle that is positive, just by definition, an angle that is positive starts with a ray, we call it its initial side, on the positive x-axis, and then its terminating ray is going to be moved counterclockwise. So that's kind of the reason why when we talk about rotations, because rotations are directly tied to circles, when we do rotations, we're always going to go counterclockwise. So to answer your question in short, we've just defined it to be that way. When we talk later on in other courses about like navigation, we move, instead of going from the positive x-axis and moving counterclockwise, we start on the positive y-axis and start talking about maybe a 200-degree angle by moving from the positive y-axis, and we move clockwise. It's just different fields of study have defined the way that they're going to do it. In mathematics, we say we're just going to go clockwise. When we do rotation, we go counterclockwise. Does that make sense, though, on how to do that problem? Okay. I want to talk briefly about this one, and mainly because I think some of you are probably getting the answer just based off of maybe visuals and not really going through the work. Okay? You might be able to look at this and say, oh, I know which one's been rotated 90 degrees just by the visualization of things. Okay? And I think that is something that's going to hamper you in regards to the end of course exam. Okay? And just being successful later on in other courses. I told the last class, I know many of people that have degrees that are much more elaborate and higher level degrees than what I have, but they're morons, okay? Because you can get a degree, you can get a diploma, you can get a high school diploma, a college degree, whatever, without getting an education. Does that make sense to everybody? Yeah. And think about maybe some of the times that you've approached Math Excel. Okay, you've gotten the grade you wanted, but you maybe didn't learn a single thing through the process of getting that grade. Would you guys agree that maybe happens sometimes? Okay, because we try, our goal is to get a good grade, right? Where our goal shouldn't be the grade, it should be the knowledge attained. Okay, because when the knowledge is attained, the byproduct is always a good grade then, right? Okay, so we got to kind of think of those things and how we address these problems, because what you're going to learn in this problem hopefully then helps us in today's work and then in tomorrow's work. But if you just do this off of a visual, say, oh, I got that, I click on this one because it looked like it, maybe I got it right, maybe I didn't get it right, I hit similar exercise, it's the exact same pictures, so I try the other one. Does that make sense? And you can get through and get the points, but did you learn anything? That's the question. So we've talked about, now this notation is a little bit different when you're using a lowercase r. Okay, they're using a lowercase r because capital R talks about reflections, right? Okay, so they're going to use lowercase so there's no confusion. But you can use capital as well. You'll see it written as capital R and then a lowercase 9, or sorry, subscript to 90. But they mean the same. So lowercase r, 90 degrees. Now that O, did we know that O stands for? It is our point of rotation, so it's the origin. And then we're going to rotate FGHJ. Well, FGHJ is a polygon that is defined by those vertices. So what I'm going to do is I'm going to know that if I have the point A, comma B, it's going to turn into negative B, comma A when I do 90 degrees counterclockwise, right? Now, what happens then is I'm going to list down, and I think doing this systematically is a good idea, meaning develop a process. So I'm going to write down these points. So F is at 0, 6. G is at negative 5, 2. H is at 3, negative 3. And then J is at 4, 3, right? So those are all my A, comma B. Well, F is going to get taken to F prime, right? G to G prime, H to H prime. Terrible, that's prime. And then J to J prime. Now look at these ordered pairs. How do you get these ordered pairs? Well, you take the original one, You flip-flop them, the x's and y's interchange, and then you negate the x, right? Okay, so when I flip-flop these, it becomes 6, 0, negate the 6. 2, negative 5, negate the 2. Negative 3, 3, negate the negative 3, and negating the negative turns into positive, right? And then 3, 4, and you'll negate the 3. So now that you have the order, so those prime ordered pairs are going to be the points that you're going to look for inside your graph, right? So I'm going to open up one of these graphs, and I'm going to look for those 4 points on the red curve, or red, not a curve, it's a polygon, okay? So look for negative 6, 0. Negative 6, 0 is not there, so it's not that one. Open up this one. Okay, negative 6, 0 is there. Now I'm going to go negative 2, negative 5, negative 2, negative 5 is there. 3, 3 is there, and then negative 3, 4 is there. So C would be my option. Does that make sense?
Yeah.
That's the best way, the best approach to do those. Okay? My philosophy is that you guys should all be able to graph by now, right? Okay? My thought then is on tests and quizzes, I'm probably going to ask questions like, if this is F, G, H, and J, tell me the ordered pair of F prime, G prime, H prime, J prime. And you should then, once you have that information, you should be able to graph F prime, G prime, H prime, J prime if needed later. Does that make sense? Okay. So that's the process there. I want to, so the next couple questions, 5 is a rotation around a point that is not the origin, which some of you might have been able to address visually. Okay, 270 degrees. Obviously, you know, if I look at this picture here, 90 degrees is probably going to be like right here, correct? Basically, what I'm going to try to do is go from D to P, and then I go 90 degrees. Well, that's probably not going to give me this picture here. 270 is not going to give me that picture there. 270, this kind of looks like maybe 180, right? Okay, so just guessing, I can probably get the right answer. Okay, I'm going to venture to say some of us were able to do that, right? Or maybe I guess wrong and hit similar exercise until I guess right. Does that make sense? Okay, so I want to show the appropriate way of doing this question, and then 7 and 8, obviously guessing on those and trying again, you're not going to be able to. You only get one option on this. They're instructor created. So this is how we do this. Okay, I'm going to write a question real quick. Come on. All right, so this is going to start the notes for today. So this will be something that you guys are going to want to follow. This is an approach that is somewhat meticulous, somewhat procedural. So you're going to have to be able to follow directions. Okay. Once we get done with the approach, I'm going to then ask you some kind of qualitative questions to allow us to create maybe a quicker process, okay? But this, I'm not just going to give you the quick process and say, have at it, because then you lose complete understanding of why that works and how then you can adjust it for maybe working with dilations, okay? So try to teach you an approach here that's going to be used several times in other transformations. And then when we're done, maybe see how we can maybe convert it into an algebraic approach. So here's what I want you to do. We're going to rotate point A, which is 6, 1, about point P, which is at 2, 3, by 90 degrees, and we'll just say counterclockwise. Yes?
When you make a graph?
I would.
You want a piece of grid paper?
Okay. Now, I think writing the question that way is useful, but you could also write this question this way. We're going to take and rotate 90 degrees around point P, be point 6, 1. Okay? So the black stuff in sentence form says exactly the same thing as the red stuff. My hopes are you understand why authors of questions and text and stuff like that would prefer to type the red stuff than the black, right? But when we become more concise with our descriptions, we lose a little bit of context, right? Okay? That's why it's important to be able to understand the notation so that when it is more concise, we don't lose meaning. Okay? I'm 100% positive about that. Okay, so now here's what we got to do. We're going to rotate point A. So we know we're going to do a 90-degree rotation. So let's just write down our rule for 90-degree rotation, because that's going to be the thing that kind of governs this entire problem. So if I go a rotation of 90 degrees, if you remember, our rotation rules are all based off the origin, right? So if I have the rotation of 90 degrees around the origin of A, comma B, it turns into negative BA. Okay? So let's kind of think about this. You can plot these things. Plot 6, 1. 1, 2, 3, 4, 5, 6, 1. And 2, 3. Okay, so we're going to draw that picture, plot those things. And I'm going to do something that I don't want you to do. So after you plot that stuff, don't do anything else yet. So I tell you to pick back up. Okay? Because this is what people do. They say, okay, you're going to rotate A 90 degrees around P. Okay. Then take A, which is at 6, 1, run it through this formula, turns into negative 1, 6, or this rule turns into negative 1, 6, and then you plot negative 1, 6. Okay? But the idea, so that would be A prime. The idea, guys, isn't it that we rotated 90 degrees?
Yeah.
Does that angle right there look like 90 degrees? No. So my hopes are that verifies, that confirms to you that the approach that we just went through right there,
it don't work.
Invalid. Does not work. So we got to have something else. Okay? Got to have something else. I'm going to explain to you the process. Okay? Trying to get you to follow along with that process. Maybe you eventually be able to mimic this process. And then once we get that done, we'll go back and try to maybe rewrite it algebraically a little bit. So, the first thing we're going to do is we're going to create what we call a pseudo origin. You guys know what the prefix pseudo means? Fake. Okay? We'll put a false set of axes in here, and we're going to set them through always the point of rotation. So, I insert those. And now P, off the black axis, P is 2, 3, right? But off the blue axis, P is what? 0, 0. Okay? Why is that nice? Because now can I redefine A off of the blue axis? A would be, if I just count from that blue P coordinate, it'd be 4, -2, right? Now, do you have a point A that you can rotate around an origin? That make sense? So now what you're going to plug into this thing is not 6, 1, it's 4, -2. Well, when I plug in A, B as 4, -2, it's going to turn into 2, 4, right? Flip the A and the B, and negate the first one. Okay? Now, plot 2, 4. Plot 2, 4 off the blue axis. Go over 1, over 2, up 1, 2, 3, 4. So that would be A prime off the blue axis, which we said is 2, 4, right? Okay, now here's my question. Did this phrase right here ever know about those blue axes that we put in? No. So when that question is being asked about 6-1 and 2-3, it's going off of the original set of axes, the original origin, right? So when I name A prime and I define its ordered pair, it better be off of that origin right there. So come back to this origin and now count to A prime. How many units do I have to go over? 4, and how many up? 7. That's my solution. Okay? Yes?
So could you just like add the coordinates, like you take it and then you do the rotation and then you add the coordinates?
Yes. Yes. So what we're doing here, so the idea hopefully is that you see that we picked up the black axes, moved them to the right 2, moved them up 3, laid them back down, got the blue axes, and then everything was redefined off that, right? And when we come up with this 0.24, essentially then we take the blue axes back out, shift them left, shift them down, replace them as the black axes, and now that 0.24 actually turned into 4.7. So the idea here is there should be an algebraic approach that can quicken this process, okay? Now, before I'm done, before I want to go into that process though, if I'm uncertain about this, that looks like a 90-degree angle, doesn't it? And we can use, because we're in the coordinate plane here, and I'm using graph paper that is pretty precise, I can guarantee that is, if it looks like a 90-degree angle, most likely it is, okay? Now, so I know I've done it right. Got the right answer here. How can we do this quicker? Okay? Let's think about this point. How did we get, let me highlight here. How did we get that point there using that coordinate and that coordinate? Okay, now the order matters, right? So you took 6 minus 2, right? So you took the coordinate, you took the x-coordinate of A minus the x-coordinate of P, right? Comma then the y-coordinate of A minus the y-coordinate of P, right? Now as we do these problems, you're not always going to have A as being the point you're rotating and P being the center of rotation or anything like that. So let's write this in a little bit more specific terms. And it's going to be kind of nasty here. But the first thing we're going to do is we're going to take, let's label this. Let me get, I just want to get a little bit more room so this looks clean. And you guys can, last class when we put this up there, it was kind of messy and cluttered. Anything for you, Dalton? Huh? It doesn't appear as though I'm going to be able to. There we go. All right, so the steps here. All right, so first thing here, step 1. In order to find the point needed to apply the rotation rule, this is the way we're going to go through this. So the 4, -2 was the point we had to find, so we can run it through the rule, right? Okay? So the way you do that, exactly what Kennison told us, is that we're going to take the x-coordinate from that, okay? So it's the x-coordinate of point A, but I'm going to call point A the point to be rotated. And that should match up to what we're being asked in the question, right? They say rotate point A. Okay? So we'll take the x-coordinate of the point to be rotated. You're going to subtract from it the x-coordinate. So we went 6 minus 2 gave us that 4, right? So it's going to be x of the point to be rotated minus the x of the center of rotation. Okay. So that's going to give me the x-coordinate of the point that I'm going to apply my rule to. Well, to find the y-coordinate, you're going to do the same thing. So you're going to go y of the point to be rotated minus the y-coordinate of your center of rotation. Okay? That is going to give you that 4, comma 2, negative 2, 4, comma negative 2. Now think about this. Just give you the specific example here. The x of the point to be rotated. Well, A was the point to be rotated. Take the x value, subtract from it the x value of your center of rotation. So it's 6 minus 2. Then you do the same thing for y. So y of the point that you're going to rotate, so it would be 1, minus the y value of the center of rotation, which would be 3. What's 6 minus 2? That's 4, right? What's 1 minus 3? That's negative 2. Okay? That is essentially the exact same thing as counting over from that blue point 0, 0, right? Because we talked about the other day that counting, the quicker way for counting is to subtract, is it not? And that's what we're doing. Okay? So, that's the first thing you're going to do. Second thing you're going to do, step 2, okay, second thing is you're going to apply your rotation rule to that previous point we just came up with. That's all written in blue there. The x point to be rotated minus the x center of rotation, comma, y point to be rotated minus y center of rotation. You're going to apply your rule to that. So that would be the 4, negative 2 for our specific example. Okay? You're going to run that through your rotation rule, whichever rotation rule you're using. Okay? Could be 90, 180, or 270. Could be counterclockwise or clockwise. Okay? You're going to determine what that rule is, and then you're going to apply it. The third thing then, you have, so that would give me, when I apply my rule, that would give me the point up here of 2, 4. Now I got to work that back. I got to work that center of rotation that we removed out. We got to work it back in, right? We removed it through subtraction. How do I work it back in? Addition. And then that addition is going to be basically saying that point is actually going to be moved back there. So then to get to 2, 4, you would actually add in that distance that you moved to the left, and you would add back in that distance that you moved down. So we're going to add back in your center of rotation. So this will be the x-coordinate of point that was rotated. Okay, so the point that was rotated would be the 2, 4, plus then the x value of your center of rotation, comma, then do the same thing for the y. So the y of the point that was rotated plus the y of your center of rotation. And that's your answer. Okay? Now, I think, obviously, it's kind of messy having all those phrases in there. What happens a lot of times as you move through, other courses, they will call that 6-1, they'll call it like x1, y1. They'll call it p, which is 2, 3, x2, y2. Instead of using phrases there, they will say, well, you're going to take x1 minus x2, comma, y1 minus y2. Okay? And that would be a rule then to get the point that you're going to rotate. You then rotate it, and then it says, okay, well, that's going to generate then this new point that's been rotated, and then we add back in the center of rotation to that, which the center of rotation would be that x1, or sorry, it'd be x2 and y2. Okay, so we could come up with rules based off the x1, y1, x2, y2, that kind of thing. Okay, I think it's more explicit writing the words out. Okay, especially the first couple times we've done this. So let's see here. Let's see how we can mimic this process. I'll try to keep the rule there so we can see this as we go through this problem. Even though I've got this rule, guys, I think it's still beneficial. Still beneficial to draw pictures, even if your pictures are not to scale. So give me an ordered pair. Okay, I heard 7-3. So let's say A is at 7-3.
9-4.
Rotated around
3-1.
Give me another. Give me something stupid.
22.
364.
Okay, 22. Okay. So let's even make let's go. So this was 7-3. Let's make it 7-3. So if I go 7-3. So would you guys agree? Now I'm not going to count accurately here. 7-3 would be in this quadrant here, right? Okay. Let's call this point P. So -13, 22 would be in this quadrant here, right? Now they're not accurate, but if I've got this process here algebraically, it shouldn't matter. How do you want to rotate it? What degree? Okay, but let's go 270. So 270. You gonna go counterclockwise or clockwise? Let's go counterclockwise. That's good. Okay. So if you remember that rule, 270 around the origin of A comma B turns into what? B comma negative A. Good. Okay. Now let's do this. Let's do it real quick. Okay, using this three-step process here. So to find the point needed to apply the rotation rule, we're going to take the x point to be rotated minus the x of the center of rotation. Well, A is the point I need to rotate, right? Okay, so take its x value and subtract from it the x value of your center of rotation. So what do I get when I do that? Okay, so let's do this in green. So when I take, you're going to go 7 minus -13, and it'll be comma. And you take your y. Okay, so that generates the ordered pair 20 comma negative 25. Now, okay, so that right there is the ordered pair that we're going to run through our rule, right? So now I'm going to take 20 negative 25. I'm going to run that through my rule. So they flip-flop, and I make the last one negative, right? So now that is the number that is going to be working here, or the ordered pair is going to be working here. So you take the x point that was rotated. That'd be the negative 25, right?
Yeah.
And you add to it then what? Negative 13. Okay, now make sure you're always adding and you put in the plus or minus that is attached to that center of rotation. Then it's going to be the y coordinate, which is negative 20, plus then 22. So what do we get when we do that? Negative 38, comma 2. Okay, so let's see what that ends up looking like. Negative 38, comma 2. Let's just kind of think about what quadrant that would be in. Negative 38 would be all the way over here somewhere, right? 2 would be just above. Does that, I mean, now the scale is messed up, but does that kind of look like we've rotated around a circle, maybe 270 degrees? Let's use, I'll show you how quick GeoGebra is at this. Okay? But we can use GeoGebra to guarantee that this process is going to work. Okay, so A, the point that, what point were we rotating? 7? 7 negative 3?
beginning point was 7, he was negative 13.22.
Huh?
Okay, 7, negative 3.
Yeah.
Okay, so A is 7, negative 3. The point of rotation, negative 13, 22, right? Okay. Now, I'm going to come over here. So I put those 2 points in. I'm going to come over to my third box up here from the right and go down to rotate around point. Click on that. I'm going to go A. A is the point I want to rotate.
Yeah.
P is the center of rotation. And now you said 270, right?
Yeah.
What's nice about this is that it allows me to
So can we use this for the test?
click on which one of what I want to clockwise or counterclockwise. So 270, hit OK. Is negative 38.2, is negative 38.2 the value that we came up with, or the order pair that we came up with? Absolutely. Okay. So are you allowed to use this on a test?
Oh, negative.
I'm not letting you use GeoGebra on this test for that mere fact that all of your dilations, rotations, translations can be done instantaneously with the click of a button. But on your homework, could you use that to check your work?
Yeah.
I would. Okay. So we can hopefully, when they ask us to rotate, like in your homework, like question 5 or 6, I think even the 7 or 8 ask you to rotate like a triangle or something like that. I would not go through that fake origin picture to rotate multiple points. Does that make sense? I would set up a little bit of a system to allow me to rotate those kind of quickly. Okay. Maybe tomorrow when we come in, I'll show you. You guys ever work with Excel?
No.
Okay, Excel is a great thing for us to maybe set up a system to rotate a bunch of points with, because it'll do the same thing over and over and over again to similar values. Okay, so in your homework, I sent you an email that has 4 or 5 questions on a worksheet to work on, and then finish the chapter, or sorry, the section 9.3 rotation assignment that's open as well in Math Excel.
You gotta type them in.
Huh? You want to come during study hall the next couple days? All right. You can come during Wildcat times, and then we can chunk up 2 or 3 Wildcat times to do that.
Okay, so I got 100% lost when you got the whole thing.
Okay. Hold on a second. Let me turn this off real quick.